Hello everyone, my name is Perla Perez and I will present to you this poster titled Manganese Oxide Films by Laser Deposition. To start with an introduction, there are various laser techniques for depositing films on transparent substrates. However, these techniques typically require the special conditions such as specific pressures, temperatures, inert environments, or oxidizing agents than, that are often carried out in vacuum chambers. For example, Pulse laser deposition. The technique we propose in this work involves transferring material from a target of interest to a transparent substrate under ambient conditions. This process takes just tens of seconds and is low cost. The characteristics acquired by the material after deposition can be primarily attributed to the power parameters and scanning speed, as well as the rate of interaction with ambient oxygen. These changes are evident in the material's optical, chemical, and physical properties. Manganese oxides were chosen for this study because they exhibit various oxidation states, many of which are used in electronic, optical, and energy storage applications. As you can see here, only a transparent substrate and the target material are required. The substrate is placed over the target, and a focused laser beam is directed perpendicularly onto the target. The laser used has a wavelength of 1064 nanometers, a pulse duration of 10 nanoseconds, and is equipped with a galvanometric mirror system that deflects the beam to scan in stroke patterns, covering a larger area. This type of laser deposition is particularly useful for directly designing devices on the transparent substrate, for example sensors or antennas, as illustrated in the images. Deposits were made using different scan speeds and pulse energies, resulting in changes to the optical properties, with coloration being the first indicator of material transformation. For these types of deposits, the laser operates above the ablation threshold, which allows for ionizing the medium, generating a plasma plume, and transferring the ablated material onto the transparent substrate. After removing the substrate, particles with the same characteristics as the deposit material are likely to concentrate. To understand how the material changes, the manganese target was analyzed using optical microscopy and Raman spectroscopy. The results indicated that the target had a native oxide layer formed due to ambient humidity, with a spectrum similar to manganese 4 oxide, featuring oxidation states of manganese 2 and manganese 3. After laser deposition, the best manganese transformation, characterized by the orange hue of manganese dioxide, was achieved with a scan speed of 1000 millimeters per second and pulse energies of approximately 77 microjoules. In contrast, using a scan speed of 10 millimeters per second and lower pulse energies of 35 microjoules tends to form the same compound as the higher speeds but with lower concentration. When combining the scan speed of 10 millimeters per second with a high pulse energy of 82 microjoules, the intense treatment results in a weak signal from the formed oxides, and the material surface appears more fused. In this case, the radiation lines are not as clearly visible. Now, regarding previously reported manganese oxides, the bands of various manganese oxides fall within the range where manganese compounds typically appear. suggesting that the obtained oxides may be a mixture of different phases of manganese dioxides, possibly including manganese trioxide hydroxide. So as conclusions, the manganese target has an active oxide layer formed by environmental exposure. Raman spectroscopy detected the presence of manganese 4 oxide prior to the laser treatment. The laser treatment was successful as the material adhered strongly to the transparent substrate and reacted with ambient oxygen, leading to oxidation. Raman spectroscopy confirmed changes in the oxidation states from manganese 2 and manganese 3 to manganese 4. The optimal oxidation of manganese oxides was achieved by adjusting the pulse energy and high scan rate. Finally, the authors would like to thank CONACYT for the financial support. And if you have any doubt, don't hesitate to contact Dr. Yasmin Esqueda, the first author, at this email.